So here is one more conceptual problem. We will read it first. A cylindrical bar magnet is placed along the axis of a circular coil. Current induced in the coil is 0 clockwise when seen from the magnet side. Clockwise or anti-clockwise, can't say. Is anti-clockwise when seen from the magnet side. So remember, in the previous problems also, I think we were talking about the flux associated with a particular coil, and only when this flux changes there is going to be an electromagnetically induced EMF in it. So he says this is the coil. It's a circular coil there and a cylindrical bar magnet. You can imagine this chalk piece to be a cylindrical bar magnet, and it is placed along the axis of the circular coil. See, this is the circular coil, this is the axis, and I have placed this cylindrical bar magnet along the axis of the circular coil. Current induced in the coil is, forget about current being induced in the coil, there is not even going to be an EMF induced in the coil, right? Why is that there is not going to be any EMF induced in the coil? Is because you have only placed the magnet along the axis. You are neither moving the magnet closer to the coil nor you are trying to move the magnet away from the coil. Had you moved the magnet towards the coil, you would have increased the number of magnetic lines of force crossing the coil, and thereby you could have increased the flux. Flux is basically the count of the magnetic lines of force. So by moving the magnet closer, you would have increased the number of lines of force crossing the coil, or you would have increased the flux, right? And there would have been a change in the flux, and therefore there would have been an EMF and then current. Had you moved the magnet away, you would have decreased the number of lines of force crossing that particular coil. There also you would have changed the flux, and then there would have been an EMF and then current. But if you only keep the magnet along the axis, there is not going to be any change in the flux linked with the coil. And when there is no change in the flux, no EMF, no current. So what is the right option here? Right option is the current induced in the coil is going to be 0. Neither it is clockwise nor anti-clockwise, nor depends on where you are standing. So one more conceptual problem for you to enjoy. A square loop of side 10 centimeters and 500 turns is placed normal to the magnetic field, which increases at the rate of 1 Tesla per second. Webers per meter square is nothing but Tesla, so 1 Tesla per second. The induced EMF is, right? So this is based on the changing of the magnetic field with time. See, I told you the flux should change basically for the EMF to be induced, and flux is defined by B dot A. So either you can change the area or you can change the magnetic field. So here he is doing the other job, right? He says a square loop of side 10 centimeters and 500 turns is placed normal to the magnetic field. So this square loop of a fixed side and a fixed number of turns is not at all going to be moved, right? So area will remain constant. Neither he is going to change the side of the square, neither he is going to convert that square into a triangle, that is by changing the area. So he has not done that job at all. So the square loop has got a fixed area and fixed number of turns, and so he is trying to change the magnetic field, and that magnetic field is continuously changing with time at the rate of 1 Tesla per second, and he wants you to write down the EMF. So what is the procedure? EMF induced is d phi by dt. Of course, minus d phi by dt, but what is the significance of the minus sign there? The significance of the minus sign is to just let you know the polarity of that induced EMF or the direction in which the current is supposed to flow. But we are only interested in the EMF here, so I have written it as E equal to d phi by dt, and phi is B dot A, so it is d by dt of BA. B dot A, correctly speaking, but here we will consider the angle between B and A to be either 0 or 180. Fine? Okay, so cos 180 would be minus 1 and cos 0 would be 1, and direction is not important. Okay, so d by dt of B dot A, that makes it A into dB by dt. Because A is constant, I have taken it outside the integral, A into dV by dt. Now put the values of A and dB by dt there. A is 10 centimeters, so I will write it as 10 into 10, which is 100, into 10 to the power of minus 4, because 100 centimeter square has to be properly converted into meter square there. So, into 10 to the power of minus 4. Let us not forget the number of turns that he is using. So, I have multiplied by 500 and then I will write dB by dt to be 1. So, the answer is, see, two zeros cancel with 10 to the power of minus 4 and the answer is 5 volts, and that makes your B option perfectly correct. So, there is a simple problem here. He has given you the flux variation with time and we are supposed to find out the current. Let me read it. So, magnetic flux phi in Webers in a closed circuit of resistance 10 ohms varies with time t in seconds as phi equal to 6t square minus 5t plus 1. The magnitude of the induced current at a specific time t is equal to 0.25 seconds from the beginning is given the 4 options there. So, again what should I repeat here is the flux associated with a particular circuit or a coil should change. Only when the flux changes there is going to be an EMF induced and that may drive the current and you can find out the current. Okay. So, we will try to see how is the flux changing with the time with the help of this function and we will differentiate it with respect to time in order to get the EMF induced. So, I will write it as E equals minus d phi by dt. And what is the significance of the minus sign? Minus sign only tells you the polarity and the direction in which the current is supposed to flow. Polarity of the EMF induced, which end will become positive, which end will become negative and all that. Okay. So, E equals minus d phi by dt, because see here the significance of the minus sign is also to highlight that this change in the flux is going to be opposed by nature. If you try to imagine a coil like this and bring the north pole of a magnet closer to the coil, this has to be opposed by nature because you are trying to bring the magnet closer, because of which the number of lines of force which are crossing the coil are increasing, the flux associated with the coil is increasing, right, and this has to be opposed because it should not perpetually happen that you just let the magnet go once by giving it some velocity towards the coil and it continues to move towards the coil accelerating, right. So, if this has not to happen and conservation of energy has to be taken care, so you are supposed to do the work in pushing the magnet closer and closer, and when you do the work and spend your energy, that is the energy which is going to be seen in the form of a current flowing through the coil. And so, what will happen when you try to push this magnet closer to the coil, this end of the coil or this face of the coil you can say will take the polarity same as this pole of the magnet. If this is the north pole of the magnet, this face will also become the north pole, and if this is the south pole of the magnet, this face will also become the south pole, right. So, this is what we mean by opposes the very cause producing it. Any change in the flux is always going to be opposed. That is the significance of the minus sign. Fine. Okay. So, E equal to minus d phi by dt, which is minus into bracket 12t minus 5, right, because derivative of phi with respect to time is 12t minus 5. Now, if you put the value of t as 0.25 there, I think you are going to get minus 2, minus 2, and minus of minus becomes plus. So, it is plus 2. So, the EMF is going to be plus 2 volts. And now V equal to IR, you can simply apply Ohm's law. So, 2 equals the current that he wants you to find out, I, and resistance is 10 ohms, and that makes your current 0.2 amperes, and that is your first option. So, here is one more problem wherein there is a magnetic field given to you and you are supposed to write down the flux. But the beauty of this problem is magnetic field has been expressed as a vector and the area is kept in a particular plane. So, I think you have to identify how is the area vector and which component of the magnetic field has to be taken for writing the flux. So, beautiful problem, very simple. Let us read this. The magnetic field in a region is B equal to 40 I cap minus 18 K cap into 10 to the power of minus 4 Tesla. See, it is a uniform magnetic field and it has been expressed as a vector. How much flux passes through a loop of 5 centimeter square area? So, area of the loop has been given and you are required to calculate the flux which passes through that particular area. But where is the area kept? 5 centimeter square area in the xy plane, right. So, how much flux passes through that particular area? Options are given. Got this? So, please remember, let me once again repeat the concept involved. Flux is given by the formula B dot A and area vector. See, B dot A means area has to be treated as a vector there, correct? And what is the direction of the area vector that you are going to consider? The direction of the area vector will be perpendicular to the area. So, if the area is placed in the xy plane, the area vector has to be taken along the z direction. Positive z or negative z does not matter, but it is always an outward normal. So, we can take it as positive z here. So, what is the area vector then? It is 5 centimeter square K cap. And which component of the magnetic field has to be taken for writing the flux? See, because you write B dot A, the I component of B has got two components there. So, I component of B makes an angle of 90 degree with the area vector, because area vector is in the k direction and I component is in the x direction. So, angle between I component of the magnetic field and your area vector is going to be 90, and if you try to write B dot A, cos theta is involved, and when theta becomes 90, cos 90 will be 0. So, there is not going to be any flux linked with the coil or any lines of force which are going to cross the coil because of the x component of the magnetic field. Right. So, let us not bother about the x component at all and we will take only the k component, that is z component. So, 18 into 10 to the power of minus 4 is what I am going to consider as the magnetic field. So, 18 into 10 to the power of minus 4, right, and into area is 5 into 10 to the power of minus 4. So, 18 into 10 to the power of minus 4 is what I am going to consider as the magnetic field, and 5 into 10 to the power of minus 4 is the area. So, answer is 90 into 10 to the power of minus 8, or you can say 900 into 10 to the power of minus 9. So, 900 nano Webers is going to be the answer. So, A is the right answer, and I hope you enjoyed this problem. Please remember, magnetic field was expressed as a vector quantity and you did not take both the components of that vector to write the flux associated with the given area. Area was kept in the xy plane. So, k cap was going to be the direction of the area vector. So, we have taken only k component of the magnetic field, and as we were only writing the lines of force which are going to cross the area and we are not particular about whether the lines cross this area from this side to that side or that side to this side. So, we did not take this minus sign into consideration. So, we were not concerned with the minus, we just wrote the number of lines of force which are going to cross that area. So, here is one more problem. This is very beautiful because, see, I every time keep telling you that the problem is very beautiful. That is just because of my love towards the subject, and I hope you too enjoy the problems there. See, here is a circuit which is given. Why I call this problem to be beautiful is, apart from your knowledge of electromagnetic induction, you should also have again a better knowledge about solving the circuits, series, parallel, right, how to use Ohm's law and how to write down the current and all those. So, let us read the problem. A rectangular loop with a sliding connector of length 1 meter is situated in a uniform magnetic field B equal to 2 Tesla. So there is a uniform magnetic field into the paper. Resistance of the connector itself is 2 ohms, and apart from that there are 2 more resistances which are connected in the network. The external force which is required to keep the connector moving with a uniform speed. See, if I were to be here in order to set this particular problem, I would have given you one more option, 0, right? Say A, B, C, D, E, and E option is 0, because a student may immediately feel that because the connector has to move with a uniform speed according to Newton's law, why should there be any force acting on that particular rod, right? But let us not forget that there is also going to be an electromagnetically induced EMF, there is going to be a current, and when the current starts flowing through a conductor which is placed in a magnetic field, it experiences a force, right? And that force has to be counterbalanced. Then only you can expect the rod to continue to move with a uniform speed of 2 meters per second. Right. So, let me completely explain you the problem now. See, this is the connector which is moving with a velocity of 2 meters per second, and it has to continue to move with a velocity of 2 meters per second. The length of the connector is 1 meter. There is a magnetic field which is uniform and of 2 Tesla which is into the paper. So, this conductor which is moving in a magnetic field will result into an EMF induced across the ends of the conductor. Do you agree with this? This conductor which is moving in a magnetic field will result into an EMF induced between the ends of the conductor. So, basically that rod which is moving in the magnetic field will act like a cell, a battery which is connected to the network of your current electricity chapter, right. So, what I will do? I will replace that connector, moving connector in a magnetic field, with a battery of the required EMF. But to find out that EMF, I hope you remember that the formula is BLV, where B is the magnetic field, L is the length of the conductor, and V is the velocity with which it is moving, right. Okay, so length is like this, velocity is like this, magnetic field is into the board. So, if you write QV cross B, V is like this and B is into the board. So, V cross B is given in the upward direction. So, all the positive charges, but remember here the charges are, I think in the previous problem also I had told you this, the charges are electrons, they are free charge carriers of a conductor which are electrons, and they being negatively charged particle, what will happen? So, QV cross B has resulted into a thumb pointing in the upward direction, but because they are electrons, they should experience the force in the downward direction. So, all the positive charges will be accumulated here and negative charges are going to be accumulated here. Got this? Okay. So, I will replace this conductor now by this connector by a battery. So, I will redraw the circuit. See, here I have drawn that battery with the positive terminal upwards and negative terminal downwards, and this stands for the internal resistance. He has given the resistance to be 2 ohms, and this is one more resistance they has included in the circuit. So, this EMF is now BVL, B stands for 2, V stands for 2 and L is 1. So, EMF of this battery will be 4, internal resistance is 2 ohms, this is 6 ohms, this is 3 ohms. See, now you have got a simple network like any other current electricity network there, wherein 6 ohms and 3 ohms are in parallel. Got this? Okay. So, their equivalent resistance happens to be 6 3s are 18 divided by 9, which is 2. So, and that 2 ohms will be directly connected to this 2 ohms in series. So, I will redraw this circuit again with only one single resistance and a battery. This resistance is of 4 ohms, right. Let me repeat here. I have added these two in parallel and I have got a resistance of 2 ohms, and that too has been clubbed with this 2, and the resulting resistance is 4 ohms, and this battery is of EMF 4. So, what current flows? The current which flows through the external circuit is 1 ampere. So, 1 ampere current is flowing through your connector, and that current is flowing from negative terminal to positive terminal through the connector. See, the direction of the current is different in the external circuit and in the battery. The current flows from positive terminal to negative terminal through the external circuit, whereas the current flows from negative terminal to positive terminal through the connector or through the battery. Okay. So now I will write the force experienced by this current carrying conductor because of the presence of a magnetic field. And I hope you recollect that whenever there is a conductor carrying a current placed in a magnetic field, it will experience the force given by the formula I dl cross B. So there is a current in the conductor, it has got some length and there is a magnetic field. So ILB, I is 1, L is 1 and B is 2. So the force is 2 newtons, ILB. Let me write it here. So force experienced by current carrying conductor is ILB, which is equal to 2 newtons. What about the direction of that force? See, I is upwards, B is into the board, so IDL cross B should be towards the left. So that force is in this direction. Now if you don't compensate this force of 2 newtons, you cannot expect this connector to continue to move with a uniform speed of 2 meters per second. And that is the reason he has asked you what external force is required to keep the connector moving with a uniform speed. So don't presume that for any body to continue to move with a uniform speed, why should there be any force acting on that particular conductor? I warned you, I could have given you an option which is 0 there. Of course, here he has taken care, you are fortunate enough that there is no option like 0, but one option could have been 0 there, but that is a wrong option. The correct answer is, it is already experiencing a force of 2 newtons and you should compensate for that. So 2 newtons force is to be applied on the connector in the direction in which it is already moving. So if you apply a force of 2 newtons in the direction of the velocity, you can expect it to continue to move with the same speed. So which is the right option there? 2 newtons, that is A option is correct. So one more conceptual problem. A small conducting circular loop is placed inside a long solenoid carrying a current. The plane of the loop contains the axis of the solenoid. If the current in the solenoid is varied, the current induced in the loop is clockwise, anti-clockwise, 0, you cannot find, the data is insufficient or something like that. See, why I call these problems to be conceptual is, you need to have an understanding about whether there is any flux associated with the loop or not is the first thing, and if that loop is changing or not. Because the very idea about electromagnetic induction is that the flux associated with an area should change, with a loop should change, right? And then only there is going to be an EMF induced, and then if there is a closed loop or a conducting path for the current, then the current will also start flowing. First requirement is EMF, and second requirement is about a path for the current. If it's an empty space, there may be an EMF induced in that space, but there is not going to be any current because there is no path for the current to flow, right? Okay. And why do I appreciate this problem more is because it is a multi-conceptual problem. You need to have an idea about the solenoid and what do you mean by long solenoid, how is the magnetic field inside the solenoid, what about the direction, how do you write the magnitude, right? So I call this problem to be important. So it helps you recollect some points about the previous chapter also. Got this? Okay. So here he is talking about a long solenoid. So let me tell you, once he says that the solenoid is long enough, when do we call the solenoid to be long? Only when its length is very, very large in comparison with the diameter of the solenoid. Then the field becomes uniform, it is restricted only to the space inside the solenoid, and it is purely along the axis of the solenoid. When he assures you that the solenoid is long, you can take for granted these three things. The field is only inside the solenoid, the field is uniform, and the field is along the axis of the solenoid. Depending on the direction of the current, of course, whether the field is going to be from here till there, if you hold the solenoid like this, solenoid is like a spring. So if you imagine the spring to be held like this, whether the field is from here till there or from there till here, that depends on how is the current. So if the current is clockwise when you are seeing the current from this side, then the field has to be away from you. If you find the current in the solenoid to be anti-clockwise, the field has to be towards you. But the field is going to be purely along the axis. Now come to the loop which you are trying to place inside the solenoid. The loop contains the axis of the solenoid. See, how is the loop? Suppose this is the solenoid like this is the axis of the solenoid, and the loop contains the plane of the loop contains the axis of the solenoid. So the plane of the loop should be, imagine that it's a circular loop. Of course, shape is not important there because he has not told you about the radius or anything. So shape is not important, but the plane of the loop contains the axis of the solenoid is what he assures. So this is the plane of the loop. Even if it's a square, you can imagine that square to be like this. If it's a circle, you can imagine the circle to be like this. So the plane of that loop is carrying the axis. So how should be the area vector of the loop? The area vector of the loop should be perpendicular to the area. So if the loop plane is like this, then the area vector will be like this. So how do you write the flux linked with that loop? B dot A. B is along the axis, area vector is perpendicular to the axis. Because the plane of the loop carries the axis, area vector is perpendicular to the axis. Angle between the magnetic field and the area vector is 90, cos 90 is 0, therefore the flux associated with the loop is 0. B dot A is 0. See, dot product involves cos theta there, and theta is 90, so flux is 0. And when the flux is 0, no question of any current being induced. If the current in the solenoid is varied, you might have varied the current in the solenoid, because of which the magnetic field produced along the axis of the solenoid may be varied. But when there is no flux going to be linked with the loop that you have placed inside, why should there be any current induced in the loop, right? So there should not be any current induced in the loop, neither it is going to be clockwise, nor it is going to be anti-clockwise, nor there is any reason why we should say that we cannot find. So the correct answer is 0. So C option is perfectly correct. So here is a very simple problem, but it will remind you of what these hot wire meters or AC meters are going to measure. So let me read the problem. He says an AC ammeter connected in series with a circuit reads 5 amperes, and he is asking you the RMS value of the current, right? So this reading which the ammeter has given to you, because it's an AC ammeter, is nothing but the RMS value itself. So don't be in a hurry to either divide this by root 2 or multiply this by root 2, because those are the options which are given there, right? The correct answer is 5 amperes. So B is the option.